from what we have checked, they give the same. Yeah. So because computing the geometric entanglement is simpler than the entanglement entropy in general, and that can actually be scaled to really large system size. So yesterday I described you that we calculate up to 100 by 100 lattice size that we were able to do. But the example that I show you, because we don't have a very well description using tensor network at the moment for the double Fibonacci ENIAC model, so therefore we do it on a small system size where we write down the wave function exactly, not using the tensor network. But maybe in the future we're thinking more systematically extending it to larger system. But as you see, just for 27 spin, the agreement is very good. Yes.
So say if I have a generic model, say J1, J2 Heisenberg model, and which I don't really know the ground state, and because then there are some methods I can search for the ground state, and there's some possible topological order state spin liquid.
So I would say first you do an exact diagonalization torus, and you find approximately degenerate ground states, and then you use those almost degenerate ground states as your basis, and then you carry out the procedure. But you may include more or fewer states, but there should be some consistent check for these modular matrices. Yeah. So, and if you were able to scale to a larger system, then these degeneracy would be much better if you were able to use tensor network to get the four or multiple degenerate ground states and use that as your superposition and carry out the minimization. Well, in general, it's not an easy task, but that at least that shows that using the same idea that you can actually not only detect topological order, but also use to give more characteristics of the corresponding phase. I think this is also done in the quantum Hall system by Donald Shen. Yeah.
So you showed two examples where the geometric entropy are different. One is totally degenerate, the other is
this one.
Right. So before you do the actual calculation, is there independent hints that you can guess the patterns of outcome?
Yeah, so the ground space of these model on torus, let's say, let me denote this as a subspace of, let's say, vacuum, and then this is has Fibonacci anyone. This is bound state, so it's known that this is dimension 2, and this is dimension 1, and this is the dimension so 1. So there is somehow you can further decompose the ground space into such a structure that the vacuum is trivial. The vacuum actually has the smallest entanglement, and if you have let's say one Fibonacci anyone, that you could, because this is double, it's from actually 2 layers in some sense, so you have dimension 2, and these are somehow deal to each other, so therefore they have the same entanglement. So you would expect that in this subspace, it's dimension 2, therefore you have 2 basis states that have the same entanglement. And the one that's more complicated has higher entanglement. So somehow it can be used to give you some hierarchy of the ground space. This is what we did not expect. For the ENIAC, the abelian ENIAC model, such as Topological and the double semion, these 4 states all have the same entanglement. So because you can actually permute these particles and they can be mapped to each other. Okay, so any more questions? So before I switch gear, I'd like to announce my collaborator, Roman Aruz, and Arthur Garcia, Oliver Schaffer, Martin Van der Nes, and also Jing Fang in the audience. Okay, so these are incomplete list of references. Basically, what I described are in these 3 papers, but I also introduced the notion from other people, and these are incomplete list of them. So I will make these slides available. Okay, so then I will switch gear to a completely different subject, namely the AKLT state for quantum computation. So I'll just take a switch. Okay, so the AQT state, okay, so I will just give some introduction, but then I continue after the break, lunch break. So, I mean, the AQT state was mentioned earlier in yesterday, and also mentioned whether it can be used for quantum computation. So, and all the organizer asked me to discuss this subject. Okay, but let me just start with really overall view by showing this slide. So you see that the number of transistors on the chip roughly double every 2 years, or you can imagine the size will shrink every 2 years, and if you extrapolate this trend, and roughly, we don't know how it really behaves, but let's try to give an estimate. It seems that at a scale of 1 nanometer, it will be reached at the year 2037, roughly. We don't know how it will go, but so that means the transistors are so close to each other that they are interacting by a quantum mechanical effect. So you cannot ignore the quantum mechanics in these transistors, even though you can shrink it. And so you would not expect that it would behave as if the behavior were separate far apart. The quantum effect would be very important. So maybe in about 25 years, we will see the end of Moore's law, or maybe even before that, because it's probably too much money to make the transistor. So the quantum regime is essentially inevitable. So this means that we have at least 25 years to think theoretically how we can make progress before we hit this barrier. Fortunately, there is a new Moore's law that's emerging, and these are based on systems that people have been working on. So let me just show you a few: trapped ions, atoms, superconducting, Joseph junctions, circuit security, cavity security, quantum dot, MMR, and NV center. And some of these systems have been awarded Nobel Prize. We could also say this also been Nobel Prize. So people already start not only thinking about these issues, but also working towards that. And this is possibly a new Moore's law that's emerging. So this is for the ion trap. And so people check from this person's website that if you record the number of qubits that you have, and it seems to, this is the explanation, 1, 2, 4, 8, 16. And it seems to follow a trend that the number of qubits in ion trap seems to double every 6 years. So you might we might have a new Moore's law, but we only have just a few years of data. So hopefully it will catch up by the year of 2037. We will have exponential number of qubits. Okay, and you would think maybe quantum computer is still far away, but what would people have thought about in a year before 46 that you could actually have a classical computer that's working, and this is quite heavy object. It occupies the whole room and has thousands of vacuum tube, and but the task it can carry out is probably much smaller than your cell phone, much smaller than your cell phone can do. Okay, so we don't know when the first generation quantum computer will appear, but hopefully we can see in our life. So let me just, how much time? I have 5 minutes. Okay, so let me just give a very brief idea of why quantum computer can work and why it's so difficult to come up with good quantum algorithms. So imagine that I have an integer function that I can actually construct using some unitary. I label u, f, which actually calculates the function of f given a value k. So suppose I can have this unitary evolution so that I take this input to that input. So now I want to consider if I can superpose my input from 0 to 2 to n minus 1. Then I apply the same gate. It's just a different input. Then I will get a huge superposition of my input and my answer. So it sort of suggests that the quantum computer is massive parallel that you could use to calculate something, although it was calculated in your quantum computer, but it's very difficult to extract the answer, because how would you get the answer? I have to perform the measurement. Suppose I measure this register, then I get some random k, I may get 2, and I compute f of 2. So in some sense, if I do this measurement naively, it looks like a classical random computer, and it's not doing exactly what I want. So therefore, there's a dilemma. I mean, quantum computer has a massive parallelism, but to read out, you need to have measurement, and measurement sort of compromise what you can do. So a good design of measurement could actually reveal the property of f. Suppose you don't need to know all the f. You just need to know its property, like the periodicity, such as used in Shor's algorithm. What you can do is be slightly smarter, and you measure the second register. Suppose you measure and you collect your wave function, you get a value, let's say 3. Then the first register will be in a superposition of those states. When you evaluate, it gives 2. So that somehow gives you more feature or more information about the function rather than the exact number itself. Okay, so using this, you can actually, by Tzu-Chieh, he designed a factoring algorithm, and we know that the factoring is hard. So just to demonstrate, can you factorize this number? And so if we had a quantum computer, this can be done very efficient. So let me just maybe end by just giving you really one-page overview of what is a quantum computing. So quantum computing is that depending on what algorithm you want to carry out, you have something in mind you want to do, and that can be implemented by, let's say, a large unitary, as I showed earlier, and you somehow initialize your state, your qubit to all 0, and then you want to go through these big U. At the end, you perform certain measurement. There's a theory of matrix that you can always decompose this exactly into a sequence of 2-qubit unitary and 1-qubit unitary. It's a network of these 2 simple elements. So for example, the element one box actually is implementing qubit rotation. For example, it's rotating the spin from one direction to the other direction. That's called arbitrary rotation. And the box that contains two lines, you only need one of them. You only need to be able to implement the self-control NOT gate. The control NOT gate is you have a control qubit and not target qubit. If the control is in one, then you flip the target qubit. Or you could also use in the control Z gate, you only flip the phase when both are one. So this probably is maybe I'll stop here, and then I'll continue after the lunch break that I want to tell you the framework why the AKLT state can be used for quantum computation. That is using the so-called measurement-based quantum computer. So I will introduce this, and then after that I will describe how we understand that the AKLT state are useful for quantum computation. Okay, so I'll stop here. Thank you.
So is there any questions?
I think people are hungry now.
Yeah, I think people are hungry, so there's a lot of discussion already. So let's thank Tzu-Chieh again. Thank you. Okay, so now it's lunch break. Please